This is a continuation on my little explanation of chemical equilibrium I showed before with the general equation of how a chemical equilibrium and an equilibrium constant can be expressed with the carbonic acid and the Bjerrum diagram. I'm gonna use another example here, namely the solution of iron 3. Iron 3, the oxidized iron can precipitate as a iron hydroxide because each hydroxide ion has one minus, so that fits the iron 3 plus component here into a solid component. But this is soluble in water and can break up in two components or in several, but one equation I will focus on here, which is the first dissolution where one hydroxide ion is released, and we have the cation here that can also be dissolved in water. So this, if I'm writing up the chemical equilibrium constant for this reaction here, I have the component on the right side, the concentration of those, so the FeOH2 plus ion multiplied the concentration of the OH minus ion, and then I should divide by the components on the left side, but this is a solid component, so that enters the equation of the chemical equilibrium constant with a 1, so that is not to be shown here, so I simply have the products over here, and if I look it up in some chemical literature, I can find a value. This one is from Water Chemistry by Snorek and Jenkins. I think it's 25 degrees, and the unit is going to be mole per liter squared, since I have two concentrations multiplied. Taking the p function to this, that becomes pk value, so the minus log, the p function, p to x is the minus log to a component. So that means I will have the minus log to this part over here, which is the minus log to the concentration of the iron hydroxide ion here, and the minus log to the concentration of the oxonium ion here. And since the K value was 10 to the minus 16, the minus log to that will be 16.7. Now I'm interested in trying to look at this one and convert that into something that has that becomes pH, and the relationship between pH and the concentration of OH minus is formed by that water can react with water acting as both an acid and a base, so I can form these two ions in equal concentrations, and the equilibrium constant of this, called Kw for water, is then equal to, since water as a solvent in higher concentrations the concentration of water doesn't change no matter what this reaction is, how that goes on. So the Kw is the concentration of the two ions multiplied together, and that is 10 to the minus 14 moles per liter squared at 25 degrees also. So that means that if I take the minus log to this, I get the pKw value, which is then 14, equals the minus log to the OH minus concentration and minus the log to the hydronium ion concentration. So looking at this, I can see, well, I can isolate this component here and say the minus log to the OH minus concentration equals 14 plus the log of the OH3O plus ion. So I substitute this into this one, getting a new equation saying 16.7 equals, I maintain this concentration of the species that I'm mostly focusing on here. And then instead of minus log here, I write 14 plus log H3O plus. This here is pH. And I should have a plus when I moved it over, but the pH is the minus log. So this is equal to minus pH, if you like. So I can write, adding this to both sides of my equation, then it becomes 16.7 plus pH equals the minus log to the concentration of the component. So, if I look at this, and I have my, I should have my 14 subtracted on both sides, so that gives me 2.7 plus pH equals this. So that's the thing that I could show in a diagram. This type of diagram, I call it a pH-PC diagram. I'll have the pH on one axis and I'll have the concentration. So this is the minus log to the concentration of a substance. In this case, my substance is the iron hydroxide ion. What I can see here is that if pH equals 2.7, let me see this, well, at a pH of 0, if you like, let's say I have 0 here. So if I'm at 0, my concentration of this substance here is equal to 10th to the minus 2.7, or I'm down to 2.7 on my logarithmic scale here. So this is the concentration at 0. If I'm moving up 1 pH, I'm dropping down 1 log scale here. So I get a line with a slope of 1 that represent my concentration of the iron here. So now I have graphically visualized the dependency of this concentration with the pH. I can draw that in a slightly nicer. I've drawn it here. I have also included the concentration of the H3O plus ion and the OH minus ion. This one being a slope of 1 naturally, because if that's the substance I have sort of pH on both axes. And since we know that the concentration of these two components multiplied together is 10 to the minus 14, that means that the log to the 2 is equal to 14. So the sum of the log to this OH minus concentration at the OH3 plus concentration at any pH is 14. So at a pH of 7, I have both of them at a concentration of 7. Going up in concentration 1 to 8, I have 6 and 8. Still, the concentration equals 14, the sum of the two log concentrations. Now, the iron here can actually give away another hydroxide ion. So there are more equations, equilibrium concentrations, if you like, in play here. For instance, this one can give away another ion, resulting in this component here. And there is an equilibrium concentration, or constant, supporting that reaction. And there's a third reaction also, because this component can give away, or can react again, and give away a third, the last oxonium ion, and there's an equilibrium describing this. So those reactions could be in the same way depicted in my pH-PC diagram. And if I do so, I get something like this. This is from this book, Snoyer and Jenkins' Water Chemistry. And what you can see here is my PC concentration, my pH, and here is the line that I drew representing the iron hydroxide. And I have other ions here, lines. I have the Fe3 plus here. I have the FeO2 plus, OH2 plus, and furthermore I could also have an ion where I get another oxonium ion attached to iron, and that gets an equilibrium situation described by this line. So the hatched area here represent the sum of all the dissolved components. So that means I have a minimum dissolution of iron 3 at a pH of, well, between 8 and 9. I have a very, very low concentration, less than 10th to the minus 10th mole per liter of the substances. And I can see as my pH go down, my solubility increases, and it starts really taking off around here, and at a pH of less than 2, I start really to see this dissolution of oxidized iron in the water. So I will have, in a very acidic water, I will be able to see, even though it's oxidized, iron getting dissolved in that water. Also, if it's very alkaline, my solubility increases, although it does not really reach the level of what I can get in the water at acidic conditions. So this is another example of how to use the knowledge about these chemical equilibria and the equilibrium constant that I need to find in the literature, and then I can show it like this.